The Stellar website is up. So what I'm distributing is also on the website right now. And we may be a little tight. I'm sorry about this. I'm missing one or two. So for everyone that was here yesterday, I'll just repeat briefly. We had 3 different modules live going on, and I just sent an email with the schedule for this week and next week. I'm Simon Belmar. I'm going to be lecturing on selection and service of structural materials. It's a little bit of a continuation of what I did last fall. So last fall I talked about manufacturing of material, processing of materials. Today I'll try to bridge it a little bit, so anybody that is not too familiar with structural materials and material science will be able to follow. And whenever you guys have questions, the last term it was really fun because we were doing a presentation and the people, well, I don't know this and I don't know that. And, questions are always welcome. From what Professor Eager said yesterday, he talked about attendance, and there was one sentence about you need to attend. What he meant is you need to attend other people's presentation. Everything else is okay. So, if you have to go to another class or you have an exam or something, then you can always review the video of the lecture, although it does take about a couple days before it gets uploaded. So it depends which, section you're following. We hope that you get it access online before the next one by this instructor. So I think that was about it for the announcement. Anything else? Okay. So what we're going to do is start with material selection. So there's always, and I've got a few examples that we'll go through at the end. There's always a number of steps that you have to take to build something. The first thing is to decide what's the performance criteria. A lot of time it is overall cost. And actually, Professor Eager's got a full 12-hour available online on material selection where he shows that for a given application, like if you're building a road, you'll use aggregate because they're really, really cheap by the ton. And when you become a little bit more sophisticated, you want to make a railroad or a railroad car, now you're using steel, structural steel, relatively low strength steel that's easy to weld and make all sorts of shapes. And then as you get a little bit more sophisticated, now we talk about a sport car, maybe you'll use more aluminum at that point. And if you're having a special design for an airplane or a Navy shuttle, then you become even more sophisticated on how you want to weight and be able to afford more expensive materials. So it's really in the back of our mind that we go and decide what material we're going to use, how it's going to be processed, that overall all we want is to do the job. If it's important that it doesn't look corroded, if it's a building exterior, then that becomes another criteria. If it doesn't matter, then you just use steel and put a coating on it, and rust a little bit, but it will hold there. So there's a lot of criteria, but generally we want to fulfill the function at a low cost. And we use a lot of steel. So again, this module on material selection, if you're interested to know more about just the steel industry in general, how you start from the ore all the way to selection and why it's so big, that's available online. I think the last live lecture was 2 years ago. So what we're going to do is more specifically talk about the steps involved if I decide to use structural steel, how I say exactly how to specify it, how I'm going to control the quality, not so much of the material. I mean, in the US, if you buy a bar of steel, most, almost all the time it will have the characteristic that you want, that you specify. What becomes more problem is in fabrication. If you need a casting done, if you need some welding done, then the quality can vary a lot depending on who's doing it. And it's very important to specify exactly what you want, otherwise you may as well just get two pieces that are fairly connected, and it won't fit necessarily your function. So as we get into the more detail of the use of material, I'll spend a little bit more time onto the mechanics and also the environmental resistance. So, and some of the reason I'm just going to show this briefly about my background. That I've worked a number of industry. I worked for an aerospace company called Bombardier Aerospace. They make like little precision jets and small aircrafts. I worked a little bit in oil and gas drilling equipment for Schlumberger. For my thesis work in exploring nanostructure and material and looking at their behavior and frictional sliding. So you see a little image in art here where essentially scratching the material and trying to find out the behavior depending on the grain structure and a number of characteristics of the tip and all that. I've done a lot of consulting work. I don't add it up too much anymore, but say if it's 80 to 100 projects per year, after 8 years, it's a lot of jobs. So it's a little bit difficult sometimes to even keep track of, oh yeah, I've done this, what was the name of this thing? But it does add up, so I hope that when we're talking about just anything related to structural material, you can assume if you have a project, you can assume that I may have done something similar at one point. I'm showing here an example just to show some of the projects we have sometimes. It's a blowout preventer valve. What it does is, if you're drilling a well, which we may stop doing in the US a little bit for now, right, with the low price of gas. But up until recently, there was a lot of exploration and new wells being drilled. So what you have is you have the drill string. It can look a little bit like this. It's going to go into a bigger hole, because you always start with a big hole on the surface and you keep going smaller and smaller. It's so deep. We're talking about a 5-mile distance all the way to the bottom of the well, approximately 5 to 8 miles. What happens is if you can't control well the pressure like it happened on the Macondo incident, then the formation will start to push into this hole that you created, and that will result in a burst in pressure on the surface. We call that a kick. So when you know that it's coming, because you've seen some of the pressure changes downhole with all of the sensors you have, you try to close that valve on the surface, the blowout preventer, but you have the drill string in it. So it's essentially trying to close on a big hole with a pipe in it. And one way to do it is called them pipe rams. So you have two of these C-shapes facing each other, and you form a seal. If you look at that schematic here at the bottom, the black is the seal. So you form a seal between the pipe and these two C-shapes, and then you also have a seal between the C-shapes and the well cavity itself. So it's a double seal to be able to hold pressure. To give you a sense, if we're talking about just water pressure from plumbing system in buildings, you're talking about 80, 100 psi. Here you could go to 10 to 15,000 psi. So it's about 100 times more pressure that you need to close on. So there are a lot of evolution over time on how they've been making these special valves, these blowout preventers. The general idea, and I can circulate this one, is a little bit like the principle of an O-ring. So you have an elastomer in the middle that is, probably the hardest elastomer you can come up with, but it still really wouldn't resist more than a few hundred psi if it wasn't for the steel that's on each side of it. So you use the steel to hold the elastomer on the inside. And one of the issues that happened on some weld-out projects I had is even if you only have a gap of say 1/8 of an inch between this metal plate that's on top and the elastomer can just extrude under the high pressure and you have a leak. Now when you start a leak, it erodes very, very quickly. So it's not possible to heal a small leak at such a high pressure. So you need to close very quickly and make sure that you don't have too much loss of this seal material before you shut the flow. And that was one thing that didn't happen in my condo. There was another issue, which is that the drill string was not located in the center, and this little schematic shows an example where the drill string is off-center, and you can have a draw preventer that will push the pipe back before you start to seal, but it's not all the designs that will accommodate that. So they had a few issues in terms of sequence and the speed that the pressure came in. Just have a look. It's not super sophisticated, but on each side it's a plate of steel that's 3/8 of an inch, and in the middle it's elastomer essentially. So if you're gonna go and design something like this, it's big, first of all. So the Christmas tree for blowout providers, you're looking at something that's about 2 feet this high, it weighs 10 tons, and it's made out of steel, yes. Are we using high strength steel because we're gonna be under very high pressure? Let's put a guess. Who says let's use high strength steel here? Who says low strength steel? Come on, guess. Yeah, okay, we have one for low. You're right. And the reason is you're going to have sour gas sometimes. You don't know. There's going to be some environment, very acidic environment. There's going to be some condition that if you use high strength steel, you could have a problem. And because we're talking about a safety piece of equipment, there's essentially a maximum hardness of the material that is specified for a lot of these components. So what it means is you just put more steel instead of putting it to the highest strength possible. Just wanted to talk a little bit about generally, if I'm involved with a project or the team is involved with a project, we do a number of things. There's always this phase where you're selecting the design and the process, and that's really what we're going to cover a lot in this class this semester. And then, of course, you can do a lot of testing. So here we were doing a full-scale test for seeing how good a connection, the welded connection was. You can go and find out the quality of the welding. That's what it is here on the right-hand side. Sometimes we skip that kind of expensive lab testing and we do more computer calculation, final element analysis to figure out what would happen under a certain condition of design and all that. And that's what we're going to talk about first today. I'm going to give you an example of an X-ray source project that I worked on, and it will essentially cover a lot of the aspects of what we're going to cover here: material selection and how to specify it, and what it means quality in terms of quality control and how it works at surface. So these X-ray target tubes are used for a lot of applications. They're used in the medical industry. The project I had was related to the TSA security system. So they were essentially working on a new X-ray unit for the check luggage. Essentially, instead of being a CAT scan that will just turn around the luggage belt and try to get the image from this, they had the sources being located at different position. It was stationary, and each source is small and essentially would provide an image over a range. So if we're looking, for example, this is the space we want to sample for the, for what's in there in the luggage. If you have 3 sources and they have a corresponding detector, so say I put the detector here for this one, I put the detector here, and then I put the detector here. So I got 3 sources and 3 detectors. What they were doing is they would use one source here. They had many detectors, but anyway, they use one source at a time, and you know, you have some image coming here, some image going across, some image maybe going in nowhere, and then they will use the current to put X-ray on the next source and the next source. So they were making more usage of a given set of detectors by having a total of 9 sources in there. So 9 sources, 3 detectors. Turns out the detectors were more expensive, so they didn't mind having more sources. Now, what was unique here is they had to turn on and off these X-ray sources 500 times a second. So in terms of just the design of the source, it's very different, because instead of just getting into what we call steady state, where you have the electrons. So what it is here, this schematic, is really how you can generate X-rays. A very conventional way is you have a filament, you discharge electron, you accelerate them at very high power, they hit a target. What do they generate? The first thing they generate is heat, and that can be a problem. And they also generate X-rays. So it's by impacting the elements that are on the target that you essentially energize them, and when they release that energy, they emit the X-rays. The system, again, would be really nice if you can just keep supplying the electrons. You have a target material here that is very high resistant to the heat. It's a tungsten alloy, and then what's in green is essentially a cooling system that picks up as much heat as possible. There's a fluid, and there's a number of channels circulating in there to try to maintain the surface temperature below a certain value. Turns out, before we got involved, there was already other people, so I can present what is in the public literature on this. This is just showing the temperature profile in Celsius of the electrons hitting in a very specific spot on the target, and you go to about 1,000 degrees centigrade, maybe 1,200. So I think there were some cases we think it was going up to 1,300 centigrade. So you're not melting steel if it was steel, but you'd be close. So that's why the selection of that target material is not only based on the ability to produce X-ray. Most metals, if you put it there, you'll get X-rays. It's really based on the ability to resist high temperature. Now, again, because they were turning this source on and off at high frequency, they were getting some cracks. So, you know, it's kind of a nice base system that they've been using, and now they were changing the condition and starting to have problems. So it forced them to go back to kind of the drawing board of what they were doing and what they may need to change. So if we go to that together just a little bit, because again, it ties into a lot of things. So the material selection. You can use tungsten. It's a good fusion temperature, although if you look at what are the characteristics? When we talk about thermal expansion here, there are a few characteristics we're interested. I'll call it the coefficient of thermal expansion. One reason that's important is this little layer of tungsten is sitting on a block of copper, because copper is a lot more conductive. So you have to be able to match these coefficients close enough. Now, of course, you have, I'll call it the yield strength at temperature. if you start deforming permanently the surface of this target at 600 hertz, it'll break very, very quickly. What else are we looking for? The conductivity, of course. Cost, yeah, you know, it is a factor. Turns out that they were adding rhenium to help mostly with this behavior here, the strength at temperature, in various quantities. Now, the second thing we talked about is the spec. Specification was, in this case, polymetallurgy, or just really a broad product. And they didn't know which one was the best, and they didn't really understand all the differences. What it means to be a broad product here, it means that the tungsten alloy was cast and then deformed. So if you start with a billet and you deform it, you roll it until you reach the thickness that you're interested in, and then you make a cutout, you got your disc, you're ready for production. Polymetallurgy is actually not all that different, because it turns out that they were making this disc that was much thicker. So they used powder of the tungsten and rhenium alloy. The good thing for them is they can make any concentration they have just by using two powder. You just put a little bit more, you put a little bit less. And then they were still deforming it to avoid having too much porosity. So even though they were using a polymetallurgy route, which you think of a kind of a free-forming process with powder, they were deforming it after the fact. So in both cases, you had the good possibility that if we're talking about our quality control here, I have, for example, a number of things I can do. I can do a hardness test. I can also do a tensile test that's going to give me my yield strength and my ultimate tensile strength. These are really nice. I can test for chemistry. Now, one problem is, what temperature am I going to do those at? It turns out they were just doing ambient temperature, which means they had no idea how the majority of the alloys, especially if you're using polymetallurgy or deformation processing, if you look at what happens when you increase the temperature for your yield strength, it is going down. And there's only so much. If this is our temperature of 1200 degrees C, say we're designing for that here, there's only so much you can use your data at ambient temperature to say anything about what will happen when you heat it up. So one reason is if the way you manage to get the right hardness and yield strength is by really deforming the material. So you strain harden it, but when you heat it up, it will soften again. And we'll go a little bit into more details of that. But just keeping that in mind, it really was just a limitation of their supply chain. So when I went and said, okay, so you're buying the material from these persons, so did they give you data about these properties? The answer was no. This is what they've given me. So what it means a lot of times is, this allows you to make sure from one batch to the other that you're getting the same material. But it's not necessarily giving you indication for the properties that ultimately you are looking for. So what is it that we're looking for? I said about yield strength at temperature because it's something that we can easily analyze for when we have this thermal model. We can turn on the deformation behavior. It's solved essentially for the state of stress in these different zones. And just perhaps for your interest, when I'm talking about the coefficient of thermal expansion, it turns out that it's about half of the coefficient of thermal expansion of copper. Now, there is a significance to that, which is the tungsten was about twice as hot as the copper underneath of it. So when you put it all together, they wanted to expand by about the same amount. So it was another reason for having copper. You could have used aluminum, you could have used other things under here, but the copper was doing the work very well because even though it was not getting as hot, it was expanding and was compatible with the little tungsten layer. The tungsten here was only less than a millimeter, so it wasn't, again, a very large quantity of material, maybe 8 millimeter in diameter. That's all you needed. So you would be willing to spend a little bit more money on your material and your process here to avoid this cracking. So let's talk a little bit. So what happens now, I think we're a little bit more into our demand capacity part. And to tell you the truth, let's say I put failure analysis here last. Very helpful to have a few broken pieces to know what the critical problems are. So you'll learn when we go into factors of safety and how you design for a bridge, how you design for a piping system, an aircraft. I'll go through how these are related, and what it comes down to at that point is, do you have service history? Because if you have service history, you know that if you control these properties here in the lab and you know your usage and it works, you're already on a good start there. You don't need to necessarily go and find out other things that I think become important with respect to cracking. You're not cracking, it's great. When there is a change here in the demand because they went from a source that was just one current that was going through. By the way, that doesn't mean there's no thermal cycle, because they do turn on and off that equipment every once in a while, whether it's between sets of luggages or if it's at the end of the day, and those thermal cycles also have a big impact on the stressors that you're generating. So what we're looking at here is, in terms of the demand, is say we have, we'll just put a round number, we have 500 hertz cycles, and then maybe we have 12 cycles per day. But these are much bigger. It turns out, under some conditions, we had a good indication that these were the ones initiating the cracks, the big cycle. But if the problem didn't show up before, it's because if you had a small crack at 12 cycles per day, it wouldn't grow very quickly. But if you can initiate a crack with this, the high stress cycles, and then continue to grow the crack under these smaller cycles from turning on and off the current, is really where the reason why they had a lot of failures. So when I talk about failures, is say they wanted the sources to go on for about 1,000 hours, I think, and some of them were going for 10, 20 to 100. So there was a big range, a lot of scatter, but they were only getting 1/10 to 100 of what they were looking to get. So it was a big step to mitigate the issue without having to change everything. They were not interested in changing these parameters because these are user parameters. They know that if they can switch quickly, they can scan more quickly. They know that the people don't want to keep the beams on day and night. And then the question is whether they'll agree that it will stay on hold for half an hour perhaps, you know, between big loads of luggages, or whether it's going to run continuously. They just didn't have a whole lot of confidence that he could tell the user, don't turn it off more than 5 times a day or something like that. So the solution, at least the strategy, was try to improve the material, that's the capacity here, or reduce the demand, but not in terms of cycle and frequency. So one options that we put forward and we've done analysis for is if you start, if you can ramp up your beam current when you turn the switch on, it doesn't have to be very long. Even for, instead of going to max power here, when you turn it on at the beginning of the day for, I think it was less than 1 second. If you put on half the power, then you get all this thermal gradient to develop and not be as steep. And then you can turn it on completely. So think about it, the first time when everything is cold and you hit that surface, now all of a sudden the target really wants to expand. It's the same when you shut it down. Now all of a sudden what's on the surface is the one that's getting the biggest temperature decrease and wants to crack. So it's in the cooling part that you get the tension on the target, and it's the other way around with respect to the substrate. I don't want to go through necessarily all the details of the cracking, but I'll say something about the failure analysis here, which is they were getting grain growth. And we'll talk a little bit about that. And they were really worried about, well, okay, what am I going to do here? Maybe the alloy isn't right, there's something going on. It shouldn't grow under the beam current and those temperatures, but it does. So what we concluded was the grain growth was just really something that happened after you had a few cracks that were going in plane of the target. So say I have the target here, and it's embedded, it's brazed essentially to a copper. And I got all sorts of cooling systems, so I have tubes coming in. It jets fluid on the inside, it's cooling it off. You have a bunch of those, it's great. If you have a crack that starts on the surface and turns, now all of a sudden what you do is you eliminate the conduction path. All of a sudden the heat's on the surface, it can't go to the copper directly. And that's where you get a local rise in temperature and you have all that grain growth. So what we had to do is look enough at these microstructures to convince ourselves that what was happening first was the cracking as opposed to the grain growth. And on, I think it was just 2 or 3 emissions that we had the cracks and the grains were still very, very small, and everybody got convinced, okay, so this is the controlling event. It's the cracking of the original microstructure as opposed to a change in microstructure followed by cracking. So knowing that, we're back here to the demand and capacity, to what we're looking for, temperature, and what you really wanted to do is avoid having that deformation. You didn't want to stretch the tungsten alloy. If you could stay in a regime where you're close to the yield strength, but you're below the yield strength, you get a very long life. But as soon as you start deforming it each cycle is where it will initiate these cracks, and now it will propagate them at 600. So it's not that our computer analysis was able to say exactly what were going to be the condition that will crack or not crack, but I could tell you that it did, you know, enable to make progress in terms of what we were interested in. We were really interested again in the yield strain at that temperature with respect to the different alloys that they could make, because you can make that better. You just use different powders, you use different concentration, but it is very different than testing for the properties that they were doing in quality control. So that was the first example. Any questions? Any comments? So we'll go through a lot more of how you do these steps, essentially. Before we do that, I wanted to tell you a little bit about materials processing.
Actually, I have a question.
Yes.
I know you said that the heated spot gets up to about 900 degrees Celsius, and you said even up to like 1300 or something. I know that the melting temperature of copper is around like 1100 or something around there.
Yep.
Roughly. Like,
Yep.
how did you guys determine how thick the tungsten needed to be such that the copper would melt beneath it?
So you have about 1200 here on the surface, and you only had about 300 centigrade at the interface down below. Yeah, it's very steep gradient. Yeah. A lot of shear stresses, and that's why the cracks were turning. Good question. It's about the demand. Okay, so any other questions? The making of metals first. So what I want to do for material selection, this is going to be, we could talk for material selection for a whole semester, okay? We'll do it in about 3 lectures. Today we're just going through some generalities. Next time, one thing I want to do is discuss a little bit more between metals and plastic. That's what we're going to do next Monday. Just try to see what are the differences, why you use one for one situation and you use the other for the other situation. As you all know, there's a big difference. One is corroding, the other one really isn't, although it will have environmental degradation. So we'll go through more details of that. What I want to do today is mostly just go through how you make the metal. Most of the time, especially for steel, which is a very large volume of fabrication, even aluminum, the aluminum foil, this is how you start, okay? You start with making a big piece that you cast, and then you keep deforming it and deforming it. Now, what is the reason why you deform it? As cast, the metal alloys have a lot of heterogeneity. What you do is you have a very different grain structure between the surface and the very core. You also have some differences in chemical concentration. The reason for the change in chemical concentration is at first you produce more or less of the pure metals. And that is based on the phase diagram that if I have just a regular alloy that has a certain melting point, so what we're doing here on the phase diagram is we have temperature, and then we have the concentration of an alloying element. By adding an alloying element, most of the time you reduce the temperature of fusion. So it becomes easier to melt and it will cool to a lower temperature before it solidifies. It's the same as salt and water. So for de-icing the roads right now, we just put a lot of salt. That is lowering the melting point. So it's the same thing for most alloying elements that you add into a metal, whether, most of them reduce the melting point. So knowing that, we know that at a certain temperature, and you don't need to understand all this, but if you want to know a little bit more, you start by forming a solid that has a concentration closer to the pure alloy, and as you keep going down and going down, you have more solute elements. Essentially, you're forming a crystal, and it doesn't really want to have all these alloying elements, so they keep getting pushed ahead of the solidification front, and we call that segregation. So now we have a solid piece, and there is a lot that needs to be done, not only to fix this problem. And fixing the problem of composition is pretty big, because what it requires is all of a sudden the alloying elements need to travel backward. So you need a lot of temperature and time for this diffusion to take place. What we generally do is we don't get the billets to just sit there in an oven, because we also want to tailor the microstructure, get very fine grains. And one way to get these fine grains into steel, for example, is to keep deforming. And you go through a certain cycle where, depending on the temperature you're at, if you're cold, you stretch the grains. If you continue at a higher temperature, you keep forming new grains, that recrystallization, and that happens in what we call hot forming, hot rolling. So when the steel is red and you're deforming it, probably nobody has been to a rolling mill. Has anybody seen it in a rolling mill? You did? Good. So it's hot, right? It's hot, and they don't have to heat it up sometimes. It's just the heat from continuing to deform that's sufficient to keep the metal hot. You deform it and you keep forming new grains. What happens then in hot rolling is you get to a certain size of grain and it just keeps reforming and reforming, and it's about the same all the time. So as long as you're in compression, you just keep deforming. That's why we roll. We can do extrusion. You can do drawing to a certain extent, but you're limited by the amount on each pass. This is really an overview. Don't get too worried. If you're interested in these types of topic, again, that was 12 hours last fall. It'll probably be the same this fall, and I'm happy to answer questions after class, probably, if you're interested in material science. In terms of our casting process, we had the problem of chemistry. We said we're going to keep it hot, deform it, and that's going to fix the grains at the same time. There is an extra process that's heat treatment that you do to a lot of alloys to tailor their microstructures. So in this case here, it's the case of steel that was just cooled fairly slowly. What you can see, it's a fairly coarse microstructure. Where the carbon is in these little lamellas, the black lamellas. When you try to deform this, it's going to be mostly these white grains, the kind of pure iron grains that you're going to deform. It's very ductile, it's easy to weld. If you go to this quench microstructure, most of the time what it is you get the steel really hot, red color, and you quench it in oil, water, or media very quickly. And if you have the, if you cool fast enough, or you have the right alloying element, you'll form this microstructure that's just completely different, right? This and this. Over here, deformation, just take my word for now, deformation is very difficult. You have a different crystal structure, and it's not a condition, as quenched steel is not a condition that we really use. In almost all the cases, if you're going through a quenching process, you're going to have tempering after the fact. And it's in the tempering that you get a combination of strength and ductility. So this process that I just outlined for you is really, really common for steel. If you have aluminum, it's very different. So aluminum, as it turns out, when you quench it, it's still really, really soft. And it is over time, by aging, that you increase the strength. It's just because, in this case, you form precipitate as opposed to forming this very complex microstructure, the martensite that I was showing here. So on steel, you have a transformation during the quenching, and on aluminum, you have a transformation after the fact, in aging. A lot of these processes apply to other alloys, but I want to just contrast, because those are two really, really big, steel and aluminum. It's useful sometimes if you say you have self-drilling fasteners, or you have a very specific wear application, to do a surface treatment on a metallic alloy. For steel, it just means you add carbon, or you add nitrogen, and you essentially can increase the strength, but just on the surface. It's very good for wear applications. Sometimes it's also good to the resistance for fatigue. We haven't really, just when I use the word fatigue, I really mean the behavior of any material when you repeatedly apply a load. One other aspect of manufacturing that is very, very important is joining. So it's very nice to think, oh, I'm going to have this pressure vessel, and I want to make it out of this alloy. Chances are you're going to have inlets and outlets to that pressure vessel, and those are going to be the ones that you have to worry about in terms of having cracks initiating and growing, because it typically comes from multiple pieces coming together. So welding is used mostly for efficiency. You know, in terms of structural aspect, I guess you can think of it, if I'm a simple mechanics, I like welding stuff because after they're welded, they don't move. Okay, the bolt doesn't get loose. I don't have to worry about it. It doesn't move. But when we're talking about a very critical application, say in aerospace, they really, really don't like welds because they're not the strongest in repeated loading. And one reason is you really melted the material back and you cool it off really, really quickly. So you definitely change a lot of things in terms of what we discussed earlier with steel and aluminum to try to optimize the material. If now you went through a whole sequence where you have a cast structure, you have segregation, you have residual stresses because you're cooling so quickly, something hot, so there's going to be tension in that weld. And that's why we don't have the time to go through this in a lot of details, but I'm showing here what happens in terms of the capacity to resist failure as a number of function of cycles, and these different lines, these are called SN curve, strength and number of cycle curve. What happens is, depending on how the weld is done, here there's no welding, so you're able to resist, say you have 10 million cycle, you're still able to resist 20,000 psi of cyclic load. But it can go down, all the way down here to 2,000. That's a factor of 10, just because you used the weld. So it's something that's very important. Now, I did bring these. So this is a knuckle for an ATV. It's aluminum, very lightweight. It's cast, and the reason is they wanted a low weight. They needed a certain amount of material, of course, because it's to resist bending. So this goes here and essentially connects the wheel to the control arms. What's in black, you got two A-frames that are under suspension to the main frame. So the piece you're looking at is this one here. It's got the bearing to the wheel. We put the hub there, and then you have attachment top and bottom. It's for a rear wheel as opposed to a front wheel, and everything here is just the suspension going up and down. They could make this for a similar price than making it out of steel, because with aluminum they use the casting. If you were to go to steel, well, you bend things and do a little bit like this, just hitch extension here or converter. This one, they use two sections of 4 different kinds. So this one is just a solid bar of steel. There's a little piece of tube that's put on, another piece of tube, and another piece of tube, all welded together. And it's just a question of cost. Welding, if you're going to do it in series, is very, very cheap. And wrought materials is also very easy and easy to control. What it means, you know, with all these welds in there, it's just this kind of mild steel that we were looking at with the deformable microstructure, and you wouldn't want to be doing this with a high strength steel. You just can't. That's what I had today. I'm happy to take questions. If you have special projects, sometimes take advantage of it. Provide free consulting. Tomorrow is going to be
Steve Lyons.
Yeah.
Tomorrow we're going to, I'm going to show you how law and material science come together. I'm going to follow Professor Eager